Welcome to class today. Today this is going to be a fairly short lecture, but it's an important one. We're going to be talking about soil water and plant water use, and basically how does the soil hold water and make it available for plant use. Now in the soil we talk about water generally in three different, well, more than three, but there's some terms that we need to define here. Let's talk first about saturation. I think we all intuitively know what saturation is. If we have a soil that's saturated, that means that all of the space that is occupied typically with either water or air is all occupied with water. This is saturation. Air dried is exactly what it states. If you take a soil, you allow it to sit out in the air, over time it's going to dry, and that's air dried. And the last one is oven dried. We talked about this a little bit when we were doing our moisture calculation, is that the typical temperature and time for a soil to reach oven dried is 105 degrees Celsius for 8 hours at least. Sometimes people take it out to 12 or 24 hours, but usually it can be done in 8 hours. Now, the difference between air dried and oven dried is that there's still a little bit of moisture. Even though a soil has been air dried, there's still a little moisture that persists around the soil particles. And so once you throw that soil into an oven, then that water, which is called, and write this down, this is an important term, hygroscopic water, is burned off of the soil. A few more terms that we need to learn about. The first one is field capacity, and the next one is permanent wilting point. So field capacity is the point at which a soil can hold water such that it will not drain anymore due to gravity. You can look up that definition in your book, but basically think of it like this. If you take a soil and you slowly saturate it, at some point that soil is going to start dripping out the bottom of let's say you have a column of soil, it's going to start dripping out of the bottom of the column. Now, to get to field capacity, you have to allow that soil to drain, and you drain it into the point to where gravity is not pulling any more water out of it. That is what we call field capacity. It's a very important term in agriculture. And then the next one that we talk about is permanent wilting point. Now, permanent wilting point is the point where it's the soil moisture content where if the soil reaches it, a plant that is trying to survive and live will be permanently wilted or stunted. So both of those are very important terms in soil science. Now the difference between field capacity and permanent wilting point, we term that the available water. So anything between field capacity and permanent wilting point is available water. Now, as you guys could probably imagine, the field capacity and permanent wilting point is different based on soil texture, right? Because we know that sandy soils don't and cannot hold nearly as much water as, say, a clay soil, and so the definition of field capacity and permanent wilting point in terms of soil moisture are different for all different soil textures. Here's an example to kind of explain what I mean. What you're looking at here on the y-axis is a loss rate. So this is how much water is being lost over time. And what you're looking at here on the x-axis is the water content. So with a sandy soil, you'll notice that as the water content increases, so does the loss rate. Okay? And this little box right here is trying to show this is the useful water. Okay, so permanent wilting point might exist right here at this water content, and field capacity might exist right here. But check out this clay soil. Okay, same thing. As the loss rate increases, as the water content increases, so does the loss rate. But you'll notice that the range of useful water is quite a bit wider than for the sand soil. And so, again, this is just another way of showing that this area right here and right here are the areas of useful water. So it's basically the difference between the water content at field capacity and the water content at permanent wilting point. That's the available water content. Now there's a few forces that move water in soil, okay? And this Greek symbol that you see here next to where it says total water potential, that Greek symbol is called psi, okay? And that's what we use to designate water potential. And there's 4 basic forces that we talk about in terms of water potential in the soil. The first one that we've already touched on a little bit is gravity, okay? This is the force of gravity that pulls soil moisture down. There is pressure potential, and we'll talk about that in detail in just a little bit. There's matrix potential and solute or osmotic potential. A little bit more on these in just a second. So the sum total of all these different forces kind of define how the soil water moves and is influenced by pressure and gravity in the soil. Okay, and this is the total water potential. Now the funny thing about this is this is a term of energy. Okay, you guys have heard the term potential energy. If you take a cup of water and place it on top of a table, that water has more energy on the table than, say, if you put the same cup of water on the floor. Okay, and so what we're trying to define here is the total water potential. What are all the forces that are acting on the soil and the soil water? Okay. Okay, so gravity, again, this is the flow downward. This is the movement of water because of gravity. Pressure potential is, you kind of think of this in terms of plant and soil differential. So, and you can think of it as the difference between the pressure in the atmosphere and in the soil as well. So think of it this way. As you go from the soil to the plant to the atmosphere, there is a pressure gradient, okay? And because there is a pressure gradient, that usually means that things flow from high pressure to low pressure. And excuse me. So things move from high pressure to low pressure. And so if you think about the soil, okay, maybe we've got a soil that's at field capacity, and then that moves into a plant, the pressure potential between those two drops, and so we get water flow into the plant. Further, the pressure potential in the atmosphere is lower than that of the plant, and so the water is drawn from the soil into the plant and then is evapotranspirated into the atmosphere. This is the pressure potential. Okay, there's a matrix potential, and you guys all know what this is. Think back to class when I talked about if you've ever stuck like a paper towel in a cup of water and you've watched the water move up the paper towel. This is because of matrix potential, okay? I told you that this has a lot to do with the capillarity and the pore size in the soil. This is matrix potential. So basically this is movement of water because of the matrix of the soil, okay? And when we talk about the matrix of the soil, we're talking about the sand, silt, and clay, and all this other stuff. So the sand, silt, and clay, the pore size can actually have a suction effect on the soil water, and so this is what we call matrix potential. And lastly is osmotic potential, And this is the potential that water moves because of a concentration of salts, usually soluble salts. And as you guys know, in chemistry, let's say that you have a semi-permeable membrane, and on one side of the membrane you have salt water, and on the other side of the membrane you have clean water. What happens is that the salt water will try to draw the clean water over to its side to try and even out the difference in salt, and so that is an osmotic potential. So basically, the same thing again. Gravity. This is most apparent when you have a soil that's been saturated, and you get downward flow of water. Pressure potential. This is the potential between the soil, the plant, and the atmosphere. Matrix potential, this is water flow when you have non-saturated conditions. So this is when water flows because it's attracted to the capillaries and the soil surfaces. And osmotic, this is where you have like a saline, that means there's salt in the soil. That's a different pressure potential in the soil. There's another note on this osmotic potential is that, let's say that you have a soil with salt in it. The reason we consider osmotic potential is that for a plant, in order to draw water out of a saline or a salty soil, it takes a lot more energy to extract it, and so that's why osmotic potential is important. Okay, again, we've talked about how we measure soil water. First of all, we've talked about gravimetric soil moisture. This is basically where we take the weight of the water and divide it by the oven-dried weight of the soil. And we express that as the wet weight minus the dry weight divided by the dry weight. And in soil science, we term this gravimetric water as theta G. This symbol right here is the Greek symbol theta, and that means soil moisture. And this G stands for gravimetric. So this is gravimetric soil moisture. We also talked about volumetric soil moisture, and basically this is the volume of water. So this is the volume of water compared to the volume of soil. This is volumetric water. And my slide here is messed up, but basically what I told you to do is that you need to take your gravimetric water content, because we can't really measure soil. We can't measure the volume of soil or the volume of water in the volume of soil. It's really hard to do. So we usually do this gravimetrically. And so what I told you to do is to take your gravimetric soil moisture and multiply it by the bulk density. And in this case, we're left with theta V. This is our volumetric soil moisture. Okay, just a different measure of water. It's based on volume rather than weight. Okay, and so in one dimension, if you think about this, we've got a depth of water and a depth of soil. And the easiest way to understand this is, a lot of the times in agriculture we measure or we talk about water in inches. And so a guy says, oh, I need to go out and apply 2 inches of water this week. Okay. Also, when we talk about soil moisture, we can express this in inches. And the way we do that is that we take this volumetric water content and simply multiply it by the soil depth. And so let's say that you have a volumetric water content of 10%, and you want to know how much is in a foot of soil. You take 10% or 0.1 times 12 inches, and you're left with 1.2 inches of water. And so that's using volumetric water content to determine how many inches of moisture are in the soil. This is very important. So here's another example for you to try at home. Let's say that you've got a 2 feet of soil, and you have 15% volumetric water. The way you do the math is you take 0.15 or 15% and multiply by 24, and you'll have to do the math. I don't have a calculator on me, but that's how you get the inches of water in that 24 inches of soil depth. Very important. Now let's talk a little bit about water flow in soil. Okay, there's 3 different types of flow that we talk about. The first type is saturated flow, and we're not going to go into too much detail here, but this is basically in a saturated soil situation. How does the water flow? And think about this. In agriculture, how often are our soils saturated? I think they go through various cycles of saturated and field capacity and unsaturated. And so this law, Darcy's law, it only applies to saturated flow. More realistically, we have unsaturated flow, which is basically we have soil that's in various states of saturation, either close to saturation or very dry, and we try to understand the flow in this unsaturated condition. And in both cases, what we're trying to describe is hydraulic conductivity, and that's expressed by the letter K. And basically, hydraulic conductivity is the rate of water movement through a medium per time. Or I guess rate is a unit of length per time. And so hydraulic conductivity is usually expressed in like inches per hour or centimeters per day, or some measurement like that, where it's a length per time. Okay, that's it for this lecture. It's only 20 minutes long, but that's fine. I will get working on the next.